Let's look at the anatomy of a modern instruction set. In this course, we will look at MIPS architecture. There could be other architectures like x86 and so on, but in this course, we look at MIPS. The execution assumption is we are going to execute one instruction at a time. This is mostly true of a single pipeline. If you have multiple pipelines, this assumption may not be true. When you talk about the state, as we previously discussed, state would refer to a linear byte addressable address space. Now this is mostly true of our memory. That is, we will be able to access our memory individual bytes at any given point in time. We can access those bytes 1 byte, 2 byte, 4 bytes and so on. Now we need a large general purpose register file. We have at least 32 entries in it. Most of the register files today, if you look at modern processors, they can range anywhere between 80 to 128. And you would have separate register files for integer, for FP, which is floating point, for multimedia, for graphic processors. So you want to separate some of these register files or vector processors and so on. You want to separate the register files so that that type of data will access the same set of registers. When you talk of operations, we talk of simple ALU operations. And these can be, as I said, addition, subtraction, multiplication, division, logical operations. We will also look at some data movement. Data movement is needed to move data from memory to the register file and from register file to the memory. Most of our data are going to reside in the memory, and what we are going to do is we are going to bring that data from the memory to our register file so that it is closer to the processor which is operating on it, and once the manipulation is completed, that data moves back to the memory. We'll also have some control transfer instructions. These are mostly what we call as branching. Branches are a very critical component of the instruction set because they define exactly where you're going to take, what is the next instruction you're going to execute. Branches are also very tricky because most often the next instruction to execute depends on the outcome of the branch instruction. And those details we'll get into as we talk in this lecture. So the operations that we're talking about is A maybe less than or equal to B operation C. B and C are two operands. We do some operation, store the value into A register. The load store architecture that we will talk about here is with register indirect addressing. That is, we will store some value in a register and then we will also use some offset so that that offset will be added to the register value to determine our effective address. And we will, as we go in the next few slides, we'll explain that. So the most important thing to remember here is the MIPS has a load store architecture. You load values into the memory and you store values, load values from memory and you store values into memory. Now you can have both 32 and 64-bit integers. You follow standard IEEE floating point system. And when it comes to instruction to binary encoding, we have a fixed width. This makes it very simple to decode. Now, if you compare MIPS to x86, then x86 has a variable number of bytes, which makes it really complex to decode the instruction. In x86, you can have instructions up to 2 bytes, 4 bytes, 8 bytes, 16 bytes, and many of the reason why they are so large in size is because they are all backward compatible. Some of them have to be compatible with legacy applications and so on, which makes it harder. Whereas in MIPS, we always have a fixed width, which makes it easy to decode, and they have regular fields, which also makes it easy to read and write values to our registers. We only allow a few formats, which is restrictive because it reduces the flexibility of the design, but it makes encoding, decoding simpler, and it makes those instructions that are very often used easier to work with. Now, if you look at the MIPS register format, the first thing we will see in MIPS 64, it has got 32 64-bit registers. It ranges from R0 up to R31. So we have 32 64-bit registers. For example, if some of you have taken my previous course on the computer organization, you would see that the QT-SPIM had registers ranging from 0 up to 31, and they were split between temporary and saved registers. These are the same registers that you are using, but each of it now is 64 bits, and there are 32 of them, obviously. Now MIPS64 also has 32 floating point registers. They are called F0 up to F31. They are 32-bit single precision, or they can also be 64-bit double precision. Now the way it works is each register is 32 bits. So if you're going to use F0, F1, F2, F3, all the 31 registers, they are considered as a single precision register. However, if you're going to use F0 and then F2, F4, F6, you skip one in between, then they are considered as 64-bit double precision. So F0 and F1 together forms a 64-bit double precision register. So you have to keep in mind that if you're using double precision, you cannot use the odd numbered register. But single precision, you can use all of them. R0 is a register. Generally, it is fixed to a value of 0. This is to provide extra flexibility to add some constant values, or if you're doing some memory access, load store access, it gives you some flexibility where you could do a pseudo indirect or a register indirect, where the value could be in the offset and you could use R0 as a fixed register, which will add more flexibility to what you're doing. So to keep in mind, R0 is a register which is always hardwired to value of 0. You cannot write anything to R0. It's always fixed to value of 0. The different data types that we can see, we have 8-bit bytes, we have 16-bit half words, 32-bit words, and 64-bit double words for integer data. Now, the way to think about this is most of our words are 32 bits or 4 bytes. This is true only in MIPS. If you change, and if you look at other architectures like x86, they may have their convention for the word. They might have 16 bits for a word. Okay? In MIPS, however, 32 bits constitute a word, 16 bits is half a word, 8 bit is of course a byte, and 64 bit are double words. MIPS follows Big Endian. This is opposed to the Little Endian that is followed in x86. Now what does it mean? Big Endian format always has the most significant byte located at the lower address. So the way to remember Big Endian is the most significant byte is at the lower address and the least significant byte is at the higher address. So the difference between this and Little Endian, in Little Endian format, the most significant byte is at the highest address. So the Big Endian format, that which is MIPS, is the lower address always constitutes the most significant byte. Now the addressing modes, the most common that are used is immediate and displacement. In the immediate addressing mode, we have the value, which is, let's say, some kind of a constant embedded in the instruction itself. For example, it could be, say, add immediate, ADDI, R1, R1, 4. What that constitutes is a fixed value of 4 is added to R1 and the value stored in R1. So that is kind of immediate addressing, where some constant forms a part of the instruction itself. We also have displacement, where we displace the offset. We have an offset which displaces the base value, and this is mostly commonly used in memory access. So for example, we would have something where we would say this is a base register and this is the offset to it. So we displace a value to find the effective address, and the way we figure that out is by adding the offset to the base value, and that determines the effective memory address. These are the two main ways in which we can access values, and these are the addressing modes available to us. Now, some of the other instruction set, for example, x86, has several addressing modes to provide more flexibility. In MIPS, we have fewer addressing modes, but that also makes it easy and convenient to decode and figure out what the instruction is.